Okay, lesson 8.1, first lesson of the unit. And this unit is over rational functions. Actually, we're going to have two units on rational functions, 8 and 9. Unit 8 is going to focus on the characteristics of these rational functions. Kind of just, what are they? What do their graphs look like? What are their features and things like that? Unit 9 will go a little bit more in depth into solving equations with rational functions, and that's when we're going to start seeing a lot of word problems. But here, for Unit 8, our purposes really are just wrapping our minds around what these rational functions look like and how they behave. Okay? So I'm going to start off here just talking about the rational parent function a little bit more in depth, because I talked about it a bit at the beginning of the year in the first unit, but we covered a lot of parent functions at that time, so I think a little quick review might be nice. Now, if you can remember all these features already, you could probably skip this part of the video, but this is just me going through the motions again. So our rational parent function is the equation y equals 1 over x. That is the parent function given right there, okay? Now, we can kind of get a general idea of what this function looks like if we make a quick little table. So I'll make x and y, and you probably already know what it looks like, but maybe let's suppose you didn't, right? The first x value I usually like to test is 0, but notice if you test 0, you get 1 divided by 0, and that's not possible. In math, we call that undefined. So I'm gonna leave that as undefined because I can't divide by 0. Now I could divide by 1, and 1 divided by 1 is 1. And I could divide by 2, so I said 1 over 2. Well, that's just 1/2, right? So, hold on, sorry, I messed that up in the table. 1 over 2, right? The input x is 2, but that's 1 over 2, so the output is 1/2. Of course, if I go to 3, I'm going to get 1/3, right? And so forth, right? 1/4, 1/5, and so forth. So I could plot these points real quick. There's nothing at 0, but at 1, it's 1. And yeah, I'm going to have to eyeball it here. At 2, it's about 1/2. And at 3, it's about 1/3. Okay? And I'm just eyeballing it there. Yeah? We could test fractional x's. Notice if I try, let's say x is 1/2, then this is 1 over 1/2. And if you can recall your division of fractions, keep the numerator, change multiplication, flip the denominator. This is 1 times 2, which is 2. So at 1/2, when x is 1/2, y is 2. Similarly, let me extend this out a little bit more. There we go. I could test 1/3 and get 3. And it's going to keep going like this. And so you can kind of see the curvature here, yeah? It's kind of bending towards the y and the x-axis like this. Now, if you think about this, right, as I go towards the right, these fractions are just going to keep smaller and smaller, right? 1/2, 1/3, 1/4, 1/5, 1/6, and so forth. So this line coming down is just going to get closer and closer and closer this way, right? But if you think about perhaps cutting a pie in half and then cutting a pie in half again and then just dividing it into smaller and smaller pieces, will you ever have 0 pie left over? Well, no, you'll always have some piece of the pie left over. So as this curve is going to be going down, 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 and can become extremely small decimals, but it's not actually going to hit 0. Similarly, if I divide by a bunch of fractions, let's say I divide by 1 over 10 billion. Oh man, how many zeros are there? Something like that, right? Well, that would be 10 billion, right? And so I could keep dividing by smaller and smaller fractions and get higher and higher numbers, which means if I'm looking at the piece of the graph kind of going towards zero, then this is just going to keep growing upwards towards infinity. Yeah? So there actually is reason for all this. Why does it kind of look like this? And that's these words here, say asymptote. Now, if you remember in Algebra 1, most likely your Algebra 1 teacher told you that an asymptote is a sort of invisible line that a function approaches but does not cross. The example in Algebra 1 is you guys do exponential functions like this, which have an asymptote here. Let me say that well, the exponential function gets close to that asymptote, but never crosses it. Funnily enough, this isn't entirely true. It's kind of watered down the truth to the point that it's a bit of a lie. You actually can cross asymptotes, and we're going to see that in Algebra 2. So perhaps let's tweak our definition of asymptote. An asymptote, it is a line that you approach, but it's the line that you approach at the ends. Okay, so as the function tends towards infinity, and I might write this down, by the way, in your notes, what I'm saying verbally right now. As the function tends towards infinity, that's where your asymptote is, right? What value does it approach? If it's approaching something, if it's getting closer to something. And the example I might give is we could have an asymptote like this, and a function's kind of doing this. And then it's getting smaller and smaller. So it's bouncing up and down, but it's getting close to a particular value, okay? We'll explore this concept more later, but I just wanted to get that out there, okay? So the thing about rational parent function is it has two asymptotes, one which is a vertical asymptote, the other which is a horizontal asymptote. Now those asymptotes for the parent function are on the x and y axis. So notice how I'm using a dashed line for the asymptote. Yeah. This indicates where the function is going. What is it approaching? Yeah. And if I zoom in here, the trend of these dots kind of looks like this. Kind of looks like so. This is really hard to draw on an iPad. Very not easy. At least not from where I'm sitting on my couch. That's my function. Man, I don't even like that. Ugh, that's just bad. Can I try that again? Will you let me try that again, please? Perhaps. Let's use a fatter edge. Like this. Yeah. That's a little bit better. Okay? Okay. And by the way, that's only half of it. Did you even think to graph into the negatives? Well, we didn't do that, did we? Notice I could graph if x was -1. Well, 1 divided by -1 is -1. So actually I have a point here as well. And I could keep going and graph at a bunch of other points, but you could kind of, I don't want to waste too much of your time. You could think of these points as mirrored over on this side. So your function on the third quadrant is going to look like that. Okay? And that's the parent function for rational. Now, let's analyze some of the features here now that we've all got it drawn here. Notice for x and y-intercept, there are none. This is because there are asymptotes here. And I can't, well, I did say I guess I could cross them, huh? But in this case, I don't. The asymptotes, the function approaches these lines, but it never touches the x or y axis. So therefore, there are no x-intercepts or y-intercepts. The vertical asymptote is on the y-axis, and to do a vertical asymptote, that's an x equals equation, since it's a vertical line. And we say x equals 0. The horizontal line is on the x-axis, which is a y equation. We say y equals 0. Now, for domain and range, perhaps this is the tricky part to explain. If you look at my graph here, if I'm looking for domain, right, left versus right, this function goes left and right towards infinity and negativity forever, meaning it would be all real numbers, except I don't touch 0 here, right? There's an asymptote here, a vertical, and I do not ever touch x equals 0. And again, this makes sense because we just said that we can't divide by 0, right? 1 over 0, that's bad. So my domain is from negative infinity to 0, parenthesis, not bracket. Bracket would mean 0 is included. And then we say union 0 to infinity. That is my domain. And we talked about union at the beginning of the year. We did, I think we did a fair amount with this. So I don't really want to cover too much from Unit 1. If you really need to review that stuff, go back to the Unit 1 videos. That's what they're there for. The range is a similar idea. If you're looking up and down, well, it's everything, all real numbers, except not y equals 0. So y equals 0 is excluded, which means the range is also negative infinity to 0, union 0 to infinity. Okay? They are both the same for the parent function. They won't always be the same. Depends on our shifts, but there you go. As for the end behavior, you can notice here, as x tends towards infinity, as x goes to the right, y goes to 0. And as x tends towards negative infinity, as it goes to the left, y tends towards 0 as well. But it's just kind of going up towards 0 for the negatives. Okay? And that's the basic features of my parent function. Nice. I think that took 10 minutes, but I think it's nice to have the solid foundation for the rational parent function. Okay, let's move on and actually talk about new stuff. Because a lot of this is just figuring out what the heck the graph of this thing looks like and blah, 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 blah. Okay, so rational functions. And I've already written a bunch of stuff here, so I would just jot this down in your notes. You should be taking notes during these videos, by the way, because they'll be useful during class and also in the future when you take pre-cal or calculus. So we got two forms that we're going to write these in. The content of this video only covers standard form, at least as far as analyzing its characteristics and drawing a graph. General form we're going to touch on more in the subsequent videos. So if you're looking at the standard form on the left here in red, it looks very familiar. It looks like our function transformations, and that's because, well, it's kind of written like that. So what I would do is, and I'm actually going to do this bottom part first, relate this to our general parent function transformations, that being a f of b times x minus c plus d, yeah? That equals if your parent function is 1 over x, then it's a over b times x minus c plus d. And so you can kind of see the similarity here and here, right? A is yet still the vertical stretch. C is the horizontal shift. D is the vertical shift. The only real difference here is if I'm using my function transformation general form, I have a b value here. The thing about rationals is your a value can cover it both. Because let's say I had 1 over 1/2 x. Well, I could take that 1/2, well, it disappeared because I'm doing a laser pointer, but I could take that 1/2 x in the bottom and move that 1/2 up and make it a 2 instead. Yeah, and that way it's just 2 over x. So your a value kind of covers the base for a and b. You don't really need to write it with the b value. But hey, who knows? Who knows? We could write it that way. Yeah? And notice h and k, much like vertex form, right? Do you remember the x minus h squared plus k, right, with your a like that? Still corresponds with c and d. So it's still that shift left and right. So anyway, the vertical asymptote of the equation is given by the equation x equals h. Whatever h is, whatever your shift right is, that's where your vertical asymptote is going to be. Think about it, right? Look, the vertical asymptote is this line at x equals 0. Now, if I shift that, let's say, right 3, and then my vertical asymptote is now here, because everything, right, all of this got shifted over right 3. So the asymptote gets shifted as well. Same idea for the horizontal asymptote. That would be y equals k. So if it gets shifted up, I could say, right, let's say it gets shifted down 3, then your asymptote will be down here. And there it is. Okay? And that's pretty much it. A is still your stretch factor, and think of A for your reflections, of course. If A is negative, we're going to have a vertical reflection. Incidentally, a vertical reflection and a horizontal reflection for rational functions, well, for simple rational functions, like the ones that look like this, because they don't all look like that. For simple rational functions, a horizontal flip or a vertical flip creates kind of the same image. So it's not a big deal specifying the difference. Okay. Oops. And then just a quick word about general form. I just want to talk about this leading into the next time's video. I will post all this stuff and talk about it again in 8.2. But the general form of a rational function, well, all a rational function is taking a polynomial and dividing it by another polynomial. So when I have p of x, that's a polynomial, divided by q of x, that's another polynomial, that's a rational function. I do go ahead and specify that q of x shouldn't be 0 because we don't want to divide by 0. So, yeah. And quick little tidbits. All vertical asymptotes, sorry, I'm yawning, it's getting a little late here. All vertical asymptotes can be found by setting the bottom polynomial, the denominator, q of x equal to 0. We will, again, I'm telling you, we will explore this next time. Don't worry about this too much right now. But essentially, you can't divide by 0. That result is undefined. And so anytime you try to divide by 0, that's going to create a vertical asymptote. Or what's known as a hole, but we're going to, again, talk about that later. The horizontal asymptotes are found by analyzing the degrees of the numerator and denominator. And when I say degrees, that means the powers. Yeah? The exponents. So I'm going to say exponents. There are 3 rules for analyzing the degrees. We're not talking about them in this video, but I'm just giving you a heads up. Lastly, if there exists a common factor that's a polynomial between our polynomials p of x and q of x, then this is going to create what's known as a hole in the graph, okay? And a hole might look something like this. Let's say I've got, I'm going to zoom in here. A hole might look like this. Whoop. Okay, that's an example of a hole. Okay, and that's pretty much it. It's basically just this little discontinuity in the graph. It's like a little gap along the line. Again, we'll talk all about it later, but I just think it'd be nice to have in your notes right now, okay? Like I said, all this video really covers is standard form. Okay, I'm going to work one practice example of analyzing a standard form equation, and then one practice of example of going from standard form to general form, okay? And that's it for this video. I know it might look a little long, but I haven't really talked about that much, actually. So let's analyze the characteristics of this function given. Got f of x equals 3 over x plus 1 plus 4. Okay. Well, we can make a little table here. X and y. But honestly, before you make a table, I would get down the vertical asymptote and horizontal asymptote. Remember, we just said that the vertical asymptote can be found right here. Just use this page as reference, yeah? X equals h is your vertical, y equals k is your horizontal. That's it, okay? It's your shift left and right, it's your shift up and down. So x plus 1, well, that's a shift left. So this shift left 1 just means that your vertical asymptote is x equals negative 1. And then the horizontal asymptote, well, this is a shift up 4. So your horizontal asymptote is y equals 4. So I'm going to make that real quick. X equals negative 1. That's the vertical asymptote. You must graph this. I need to see your asymptotes. These are key features of the graph. In fact, this is probably more important than anything on your graph, is seeing where the asymptotes are. There they are. Okay? Now, x and y intercept. I think that would be a good idea to find those. You know how to find an x-intercept, though, right? An x-intercept occurs when y equals 0. So can we set this function equal to 0 and find the x-intercept? Yeah. Say x-intercept. Says 0 equals 3 over x plus 1 plus 4. Let me zoom in here so you can actually see what I'm doing here. And then we'll just solve for x. Subtract 4 to the other side. I can multiply x plus 1 to the other side to get it out of that denominator. Yeah. Distribute that 4, or actually just divide by negative 4. That'd be easier. Don't distribute. That's lame. And so therefore, this is my curly little arrow here. Then I got x plus 1 equals negative 3/4. I'll subtract 1 from that, yielding x equals negative 1 and negative 3/4, which is really just negative 7/4. Okay? So your x-intercept is at negative 7/4, comma 0. And I think that makes sense. Yeah. Yeah. So let's graph that. That's about negative 1 3/4, which is negative 1 3/4. Probably about right here. Not quite at negative 2. Yeah? Nice. And the y-intercept, well, that's easy. Oh, we always love y-intercept. To find y-intercept, you just plug in x equals 0. Oh, I love those. This is just 3 over 0 plus 1 plus 4. So that's just 3 plus 4, which equals 7. So my y-intercept is at 0, comma 7. Putting that point right there. Okay? Beautiful. Look at that. We could test a couple more points. And we can put these in our table, like so. We could test some more stuff. What I want to tell you, you know how I was picky in the last unit about finding whole number values? Well, this is kind of the fractions unit. It's basically going to be impossible to find. Well, I shouldn't say impossible, but sometimes it'll be really hard to find more than 1 point or 2 points that comes out pretty. And that's fine. So the true features that matter when graphing here are your asymptotes and finding the x and y intercepts. If you can find those, that's good enough. All right, maybe find a few extra points for fun, but those are the key features I'll be looking for when grading tests. Are you graphing these key features of your graph? Look, I'll find a couple more points, though. I can divide 3 by 3. So if I put x equals 2, that's 3 over 2 plus 1, which equals 1, right? Plus 4, which is 5. So 2 comma 5 is a pretty point. Like so. Oh, that's not 5. That's 5. Okay. Yeah, that's okay. And then maybe if I do 3 divided by negative 3, so I could test negative 4. That'd be negative 1, and then plus 4 is 3. So negative 4 comma 3. Kind of like that. Could I find any more? Well, if I could try, but they're going to get fractional values. So I think that's good enough. Let's call it there and make our curvature. Yeah. All right. Beautiful. Look at that. Nice. All right. Let's quickly analyze domain and range and end behavior. The domain is, well, it's all real numbers except for your vertical asymptote, which is negative 1. You're basically going to skip that vertical asymptote and then continue towards infinity. For range, it's all real numbers except you're going to skip 4. Go from 4 to infinity. We've already did this, right? This was the hard part of Unit 1, which you already did. So a lot of this is just remembering that. Okay? End behavior. As x approaches infinity, y is getting close to the horizontal asymptote, which is at 4. Same is true as x goes to negative infinity, y goes to 4. Okay? Yeah. Your end behavior, it's always going to be approaching infinity and negative infinity, and it'll always approach the horizontal asymptote because, well, that's literally what the point of the asymptote is. It's what it's approaching. So there you go. Okay, one more example, and then the video's over. Yeah? Convert the standard form rational function given below into general form. Now, all the stuff I've been talking about prior, we haven't even done this. I haven't even set this up. But I'll tell you, you don't really need me to set this up. The idea is we're trying to convert this into a single polynomial divided by another polynomial. This is just getting a common denominator. And I'm just going to write that. I'm going to star that. All this is getting a common denominator. That's it. Okay? So how do you get a common denominator? Quick recap for you, yeah? Here's the fraction 3/4 plus 5. How do I get a common denominator? I multiply 5 by the denominator of the other fraction. So 3/4 plus 5 times 4/4, which is 3/4 plus 5 times 4 is 20/4. And then, now that they have common denominators, I can add. Yeah? Okay. Exact same premise, but now your denominator is x plus 1. Okay? Exact same premise. No different. Your denominator is x plus 1. So I'm going to say 3 over x plus 1 plus 4 times x plus 1 over x plus 1. This equals 3 over x plus 1 plus 4 times x plus 1 over x plus 1. So you can add this, right? Because now they have a common denominator, 3 plus 4 x plus 1 over x plus 1. And we'll distribute that, 3 plus 4x plus 4 over x plus 1. Finalizing this as 3 plus 4 is 7, so this is 4x plus 7 over x plus 1. Boom. Didn't want a trapezoid. Thank you. I want the rectangle, please. Thank you. Okay. And that's it. Hopefully I didn't go too fast there. But it truly is just getting a common denominator. Okay? If you remember how to do that from middle school, just multiply whatever doesn't have that denominator. Just multiply it on top and bottom. Now that they have the common denominator, you can add them together. Okay? And notice, this is now a polynomial divided by another polynomial. So, we're going to be going from standard form to rational, or to general form, just for the heck of it sometimes. You're usually going to see these things in general form, but sometimes you'll see it in standard form, and they're pretty easy to analyze when they're in standard form. So, yeah, okay. That's everything we needed to talk about for 8.1. I hope that wasn't too long. I think the information is pretty basic for now. I'll tell you, the unit's not basic. It's going to get a lot harder in 8.2. But for now, if you remember your parent function transformations, this ain't that bad. Yeah? Here are some practice questions. I'll leave the screen on here for just a second for you to look at. I do recommend doing both of these before coming to class next time. Okay? 2 questions. That's it. That's all I got for you. Can you graph this and blah, blah, blah. If you need to, even if you just sketch it on scratch paper, that's okay. All right? Just get the practice in. Find a little bit of a table. It doesn't have to be a crazy table with 10 points on it. Just find a few points. See if you can figure out the x and y intercept. Definitely plot the vertical and horizontal asymptotes and just analyze it like that. Okay, well, hope you enjoyed the video, and I will see you guys around.